All right, let's talk a little bit more about buffers, what makes a good buffer. So, for a good buffer, you should be able to neutralize moderate amounts of acid or base. But there's always going to be a limit about how much you can add before you get a pH jump. That limit is called the buffering capacity. It's the amount of acid or base a buffer can neutralize, and the buffering range is the range that the buffer can be effective. So how effective a buffer is going to depend on the relative amounts of acid and base and the absolute concentrations of acid and base. Now, there are some times where you want to be more effective against added acid or more effective against added base, and that's going to change the ratio that you would use. So a concentrated buffer is going to be able to neutralize more added acid or base than a dilute buffer, simply because there are more acid and conjugate base particles around. A buffer is most effective when your ratio of conjugate base to acid is 1. You have equal concentrations. And it's most effective within 1 pH unit of the pKa. And it's going to be most effective when your concentrations are large. Remember, with the base equal to the acid, that's going to be at your pKa value. Now, let's talk a little bit about titration. In a titration, you have a solution of unknown concentration called the titrant that's slowly added, to which is slowly added a solution of known concentration from a burette. You might use an indicator to determine the end point where you have equal amounts of acid and base, or you might use a pH meter to graph what's happening. So when your moles of acid are equal to your moles of base, the titration has reached its equivalence point, which means you've added enough of, enough base to neutralize all of your acid. Let's look at what a graph looks like of it. Here we are adding NaOH and we are monitoring our pH. So before, in our beaker, we have extra acid around. You can see we're at a nice low pH. Here we're titrating a strong acid, hydrochloric acid, with sodium hydroxide, a strong base. And then all of a sudden, our amounts of acid and base become close and then exactly equal, and then we end up into our excess base range. So our equivalence point here for this particular titration is at pH 7. That's only because it's strong and strong, but it's always where we have equal moles of the acid we started with and the base we're adding. All right, so calculate the pH of a solution that results when 100 milliliters of 0.15 molar sodium hydroxide is added to 50 milliliters of 0.25 molar nitric acid. So here we can think of this as a titration. So we have a beaker here with 50 milliliters of 0.25 molar nitric acid. We've added 100 milliliters of 0.15 molar sodium hydroxide. What we need to do is figure out how many moles of each we have and then react them. So basically our reaction here, because they're both strong, is H plus OH minus reacts to form water. This is not an equilibrium situation. These are strong acids and bases. So if we have 100 milliliters of 0.15 molar, we can calculate either the moles, or what I'm going to actually do is millimoles. So there I'm not going to convert my milliliters over to liters. I'm just going to do 100 times 0.15 gets me 15 millimoles of my hydroxide. I just keep the milli. It's just going to save me some time. And then 50 times 0.25 tells me that I have 12 0.5 millimoles of my H+. So when I react, all of my H+ is going to go over, so I'm going to make 12.5 millimoles of water. That's not going to affect my pH. Then in that 12.5, I'm going to use up 12.5 of my OH, leaving me with 2.5 millimoles of hydroxide left over after my reaction. That 2.5 millimoles is now in 100 plus 50, 150 milliliters. The millis cancel out, so if I take 2.5 divided by 150, I get 1.67 times 10 to the minus 2 molar hydroxide. So then my POH is the negative log of that value, which is 1.78, which means my pH is 14 minus that, which is 12.22. So you can see what I did is I basically just used stoichiometry. I calculated how many millimoles of each I had, I reacted them fully, and then I used what was left over to figure out my pH. So 12.23. All right, when we titrate a weak acid with a strong base, our titration curve is going to look a little bit different at both the equivalence point and in the excess acid region. So the initial pH is we're going to have to use the Ka of the weak acid to figure that out. The pH in our excess acid region, we're going to consider it like we would a buffer because we're going to have both acid and conjugate base around that's formed by adding the base to it. And then the pH at the equivalence point, we've transferred all of our acid over to conjugate base. And then since we still have that conjugate base around, that's going to affect our pH at our equivalence point. It's not going to be at 7, it's going to be a little bit higher than 7. And then the pH after the equivalence point, we're just going to have excess strong base, so we can ignore our conjugate base anion and just figure out our pH from the conjugate or from the excess base. Okay, so we're going to work through an example where we are titrating acetic acid with sodium hydroxide. We have our Ka of acetic acid. We're going to start with 25 milliliters of 0.50 molar acetic acid, and we're titrating in, this is supposed to be a burette here, 0.25 molar sodium hydroxide, and we want to look at the pH at these different points. So the way I'm going to do this is I'm going to talk through the math for all of these, and I will be referencing back to this slide that we're looking at right now, but I'm just going to pull up blank pages for us to look at. All right, so for our initial pH, we are going to have C2H3O2 plus water is in equilibrium with H3O plus C2H3O2 minus. This is simply a equilibrium situation like we talked about in the last chapter. And so we have our initial concentration is 0.50 molar, none of these, minus X plus X plus X. So at our equivalence point, we're not at our equivalence point. In our initial beaker, we have our Ka 1.76 times 10 to the minus 5, again that's from the previous slide, is equal to our x squared over 0.5. So our x value is 2.96 times 10 to the minus 3. So our pH is 2.53. So I'm going to go back a page and write that down. Okay, now we're going to do, after adding 25 milliliters of sodium hydroxide. So when we add sodium hydroxide, we have our acid plus OH minus is going to fully react to give us now our conjugate base plus water. So we've added 25 milliliters of 0.25 molar, which means we have 6.25 millimoles of hydroxide, and we started with 25 milliliters of 0.5 molar acetic acid, so we have 12.5 millimoles of acetic acid. After we fully react this, all of my hydroxide is going to go over to conjugate base. So we're going to have 6.25 millimoles of conjugate base. We've lost 6.25 millimoles from our, oh, sorry, I should write this down here. Boop. So this is 6.25 millimoles. We've lost it over here, so 12.5 minus 6.25 is 6.25 millimoles. And so now we're at an equilibrium situation where we have equal numbers of millimoles of each of our acid and conjugate base. So I can use the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of the base over the acid. Because they're equal to each other, we're actually at the point where my pH is going to equal my pKa, and to get the pKa, we're going to take the negative log of our Ka value, which again is on a couple slides back, 1.76 times 10 to the minus 5, which is 4.75, which is my pH after adding 25 milliliters. So I'm going to go back a bunch of slides by now and write 4.75 right there. Okay, then what about after adding 49 milliliters of sodium hydroxide? So 49 milliliters of NaOH. Again, oh, there's no minus right there, O2, it's a 2 plus NaOH goes to C2H3O2 minus plus water. Again, I can just start with my 12.5 millimoles that I already calculated. My sodium hydroxide, now I am taking 49 times 0.25, gets me 12.25 millimoles. After I react, now I'm going to have 12.25 millimoles over there. I'm going to have 0.25 millimoles on that side. I can still use my Henderson-Hasselbalch, so my pH is going to be 4.75 plus the log of 12.25 over 0.25. So my pH here is 6.44. So I can go back here, right in my 6.44. Then after adding 50 milliliters, let's check there. So when I've added 50 milliliters, again, plus NaOH reacts C2H3O2 minus plus water, 12.5 millimoles. And now 50 times 0.25 is also 12.5 millimoles. So I can react exactly, and I'm going to end up with 12.5 millimoles of my conjugate base and not have any acid left over. This is my equivalence point. I have exactly equal numbers of weak acid and conjugate base. But to find my pH, now I have a weak base and a significant amount of it around. So now I have to think about the equilibrium of my weak base with water. So C2H3O2 minus plus water, equilibrium situation, HC2H3O2 plus hydroxide. I have to go back to concentration. So I started with 25 milliliters, added 50, so I have 12.5 millimoles in 75 milliliters, which, if I do that math, gets me 0.167 molar. And then I'm doing an ice table now, so that's my initial. My change, I'm going to be minus x plus x plus x. So 0.167 minus x, which again is going to be x's small approximation. Now I know, if I scroll down a little bit, my KB is going to be my OH, HC2H3O2, C2H3O2 minus. So it's going to be x squared over 0.167. Now what's my KB? My Ka is 1.76 times 10 to the minus 5. So my KB is going to be Kw, which is 1 times 10 to the minus 14, divided by 1.76 times 10 to the minus 5, which is 5.68 times 10 to the minus 10th is equal to x squared over 0.167. So my x is 9.74 times 10 to the minus 6th. So my POH is 5.01, and my pH is 8.98, 8.99. So you can see when we're titrating a weak acid, our equivalence point ends up at a acidic pH. What happens after I can kind of combine these two? It's going to be the same math. After adding, say, 51 milliliters of sodium hydroxide. So 51 milliliters. Let me switch back to this color. Now, write this out again. Goes to C2H3O2 minus plus water. So we started off with 12.5 millimoles of that. Now we've added 51 milliliters, so 51 times my 0.25 molar gets me 12.75 millimoles of that. When I react it, I'm going to have 0 here. I'm going to have 0.75 millimoles there, and I will have 12.5 millimoles of my conjugate. But my excess hydroxide is going to drive my pH. So if I have 0.75 millimoles in 51 plus 25 is 76 milliliters, I'm going to have 9.86 or 87 really times 10 to the negative third molar hydroxide. So my pOH is driven simply by that. So I can take the negative log of that and find my pOH is 2, which means my pH is now up at 12. So you can see that adding that 1 extra milliliter made my pH jump. One more. From 9 to 12. And it completely dominated that conjugate base. Let's look at the graph here a second. So you can see we have this big, if I plot a bunch of those points, we get this big jump here, and then once we've added that much, our pH kind of is completely dominated by the hydroxide, so we don't have to take the conjugate into account except exactly at that equivalence point. Then at the half equivalence point, which we also calculated, is where my pH is equal to my pKa value, because we have equal amounts of weak acid and its conjugate base.